All right, good morning. So we're here at 9 a.m., so hopefully we are the hardcore people who can understand advanced macro topics. I have to apologize in advance if you're not already familiar with Racket's macros, because this will be a little bit of a wild ride. So we've seen uses of Syntax-spec, which is the system that I built for my PhD, in other talks already. And I gave a talk about it last year from a design idea perspective. So this year I wanted to give a talk about it from sort of an implementation perspective. What's happening under the hood of Syntax-spec? And so the way I'm going to do that is I'm going to sort of build up to code that is similar to the code that Syntax-spec generates for you. So that you can kind of see the patterns of macro programming that are sitting underneath. And you can also see why maybe you don't want to write code using those patterns yourself by hand. And you might prefer something like Syntax-spec to generate it for you. So our goal today is we're going to start with an embedded DSL, just a DSL using functions and data. And we're going to try and create a macro layer over that DSL that lets us implement a few things that go well beyond just having pretty syntax for it. So we're going to try and enforce that our programs follow the grammar that they're meant to and give nice static errors if they don't. We're going to try and create DSL name bindings and check references to those, make sure those are correct. We're going to perform a compiler optimization, and we're going to do this all in a way that would support macro extensibility if we had time to get there. So that's going to mean that we have to, interoperate with hygiene and those other things. So we're going to build up to this with 4 different strategies of implementing this DSL, and the last strategy is going to be building out with Syntax-spec. All right. Let's dive into the DSL. So this is the sort of primitive version of the DSL that we're going to start with. So it's something like SQL or LINQ in C# or F#, where it's a query language that sits inside your programs and queries data from your programming language. So in this case, it's a query where we're going to select some columns from a table called routes, and we're going to ask for only 5 of them. And here our table called routes is something we loaded from a CSV. And the data type that we start with is really just a list of hash maps. That's the kind of data that we're going to work with. And the query language here is going to work by processing streams. So in the embedded version of this, every clause, like select or limit, is going to have the type of stream of row, where row is one of those hash maps representing a row, to stream of row. And this overall query form is just going to sort of apply each of these transformations on the stream entirely. So that's the initial language that we're going to start with. Let's run it. So we can see the kind of data that we get back, this list of hashes. So we're able already to implement a DSL, something that feels like a DSL, just writing Racket code in a particular stylized way. And let's look at a slightly fancier example of this DSL. So here's a query where we have some filters and we have a join. So the idea here is our database is a database of airlines and routes that those airlines fly. And this particular query is finding all of the routes listed by American Airlines, but that are code share routes. That's the other field here, which means they're actually flown by somebody else. And to get that, we have to first select from the routes, which is our original from routes at the top. But then we also have to join with the airlines table so that we can sort of map between the foreign key airline ID and the actual name of the airline so that we can write out a simple query. All right, so that's the kind of thing that we can ask so far. This particular query has to churn through a lot of data, so it actually takes some time, a few seconds. But there are some drawbacks of the DSL as we have it expressed so far. So let's look at a couple. So one is that we're expressing our query in terms of Racket function calls, lambdas, data. So it doesn't sort of feel quite like a language. We're having to quote these column names when really we're thinking of them sort of as identifiers in our syntax. When we do the predicates, we always have this pattern of where and then lambda row to bring the row identifier in scope. So there's some syntactic overhead from there. So those are sort of shallow problems, which we'll find easy to fix. But then there are some also deeper problems. So one deeper problem is that if I misuse the syntax, you'll notice right now I have background expansion on, and nothing went wrong. So what happened was I put the select before the from, but according to sort of the grammar I have in mind for my DSL, that doesn't make any sense. I have to start with data, and then I can project out columns if I want. But with the embedding, if I run check syntax, nothing is going to happen. The only time I'm going to get an error is at runtime with some sort of Baroque problem. So our embedding, at least in a untyped language, is not the best. And then our other problem is that we have abdicated the possibility of performing any optimizations when we implement in this way. So the query that we wrote is on the top here, but it turns out that we should have, if we were really clever, expressed it in the way at the bottom, where this where clause, which was previously after the join, moved before the join. And that's because the code share column that we're referring to here comes from the routes table, doesn't come from the airlines table. And so there's no reason to wait until after the join to filter. And so if we do this optimization, it turns out that our query can be much, much faster. But we need our macro to help us do that. So those are the sorts of improvements that we're going to try and make with our series of implementations. So let's get started with the first one. So our first step is going to be to add a little bit of syntactic sugar, just so that our queries look nicer. So here's going to be our new syntax up top, and at bottom is what it's going to expand into. And a couple of things to note is that in the syntax up top, we don't have to quote our column names anymore. They look like identifiers. And for the where clauses, we don't have to have this lambda row anymore. Instead, we're going to access the columns with this call macro that's going to magically somehow access the row. So this is the first layer of improvement that we're going to make. Let's see how we can do that. All right, so we're going to start with fairly conventional macros. The strategy I would call macro embedding. Maybe there's a better name for it, but we're going to make a separate macro for each syntactic form. And the most basic thing would be, for example, transforming select, where we don't have quotes, to select with quotes, right? So we're just going to define a macro called select, and it's going to expand to the runtime select, but it's also going to add a quote before the columns. Super basic. So slightly less basic is handling the where. So the transformation for where that we want is we want to have this expression where we use where and call somehow expand out to this expression where introduces the row and call somehow hash refs the row, right? So that's not quite an independent expansion of where and call. We need to cooperate a little bit to implement that expansion. So if we look at how this is going to work in a little bit more detail with an intermediate step, we're going to use what's called a syntax parameter, which is where we can change the meaning of a macro in a local context. So where is going to step to this intermediate expansion, where it introduces this syntax parameterize, which is going to change the meaning of the call macro by giving it a new transformer. And that transformer is going to have the row identifier built in, so that when we reach this call reference down here, the call macro that we have now is going to know about the row identifier, and we'll be able to expand here to the hash ref of row. So here's the implementation of that. The where macro does the expansion that we just saw. We define the syntax parameter whose initial value says, well, I don't make any sense if I'm outside of where because I need the row. So raises an error if it's not used in where. And then we define that transformer that's parameterized by the particular row provided by where, and we use it to insert the hash rows. So together, this gives us our first somewhat syntactic sugary syntax that looks nicer. We're happy with sort of the look of the syntax, but we still haven't really solved our other problems. So there's still no check that we followed the grammar correctly. We still don't have binding structure, so we still can't actually tell that, for example, code share comes from routes instead of from airlines, right? So we can't perform our optimization. So let's try and take one more step. So we're going to have a different syntax now. So this is the syntax that we'd like to implement. So the difference here is that when we refer to a table, like from routes, we're actually going to name all of the columns that we're going to use from that table right there. And that's going to mean that when we refer to them later, we have bindings for them, and we can tell sort of which table they correspond to. And we're going to try and do this in a way that DrRacket understands the binding structure, can draw these arrows from us. And also we're going to try and do it in a way where we get a syntax error if we misuse this language. So in this version, if I uncomment this, we'll fairly immediately get a pop-up down here that says bad syntax in query. If I check syntax, we'll see that. I guess I didn't get the highlighting location quite right. So that's the second thing we're going to try to. So in order to implement this, we have to step back and take a somewhat different strategy. Before, we were thinking about translating each individual syntactic form sort of independently to a Racket expression. But now, since we want to enforce a grammar, do this binding, we're going to have to take responsibility for a little bit more over from the Racket expander. So we're going to have to create an expansion structure that follows our grammar to enforce it instead of enforcing the Racket grammar, which isn't sort of precise enough here. All right, so strategy 2, I don't have a good name for it again. I'm going to call it recursive rewriting. What we're going to do is we're going to use a set of sort of mutually recursive macros, one per grammar non-terminal, to rewrite the syntax. And then we're going to handle DSL name lining by introducing Racket let syntax bindings that are going to bind the DSL names as macro transformers, which we can identify later by reflecting. So let's look at an example of how this is going to work. So if we have this somewhat simplified query where we're just selecting from routes, the first step of expansion is going to take us to this rather large form. And there are a couple of things to note about it. The first is that as part of the expansion of the overall query, there's a call left over that I haven't expanded yet, a macro invocation that I haven't yet expanded, that's going to compile clauses. So clauses is sort of one of the non-terminals in the grammar that I'm thinking about for my DSL. And I haven't expanded, this is unexpanded DSL syntax that I haven't compiled into Racket yet. So each step is going to compile a fragment and then call another macro corresponding to the grammar non-terminal for the remaining syntax that we want to compile. So that's one thing that's going on here. That's how we're enforcing grammar. The second thing that's going on here is that our column names, so that's source airport and destination airport, these are getting bound as macro bindings, with the transformer value being one of these column binding representations. And I'll tell you a little bit more about exactly what that is in a minute. But we're binding them as macros, and that's going to mean that later when we see those references, we can identify them. So the second expansion step, let's sort of zoom a little bit forward. After we go ahead and compile the clauses, what are we going to end up with? Well, we're going to still have our let syntax, we're going to have a bunch of runtime fragments, and then there's sort of two interesting things. One is the reference to the source airport name, and that sits inside the where clause. And the other reference is to the destination airport, and that sits inside of our select syntax. So we actually want to do two different things in this case. So in the case of select, we just want to end up quoting destination airport, but we actually want to make sure that that's a valid column name first, right? We're trying to implement that static check that our reference column names are actually valid column names. So we're going to have some macro that's going to somehow check that destination airport actually got bound up here by our let syntaxes, right? And then the other thing is this context where we have this equal source airport Boston, this is sort of not a DSL context anymore. We've escaped back into Racket, and we're using Racket to write this predicate. So this is a reference to a DSL name from a Racket context. And we actually want to transform that one differently. We're going to transform that one to access the column from the row in that predicate. So the way we do these two things requires that we tell the Racket macro expander that these column bindings are a different kind of thing. So normally when we put something in the expander environment, the kind of thing that we put in is usually a function, right? Function from syntax to syntax. It's a macro. And so the expander knows that when it comes to a reference to that, it should apply the macro. But we want to put a different kind of thing in here because we want to identify something that's not exactly a macro, but it's a different kind of syntax. It's one of our DSL name bindings. So what we're going to put in is we're going to put in an instance of a structure. So I'm going to jump down to the definition of that structure. So the thing that's on the right-hand side of our let syntax is an instance of the structure. It's a distinguished type so that we can recognize it later. So then when we want to check a reference, so this was like a call to checked ref of destination airport, something like that. We want to check that destination airport was actually bound as one of these column bindings. So to do that, what we have to do is we have to look it up in the Racket expander environment. So the expander, kind of like an environment passing interpreter or something, passes along an environment of the knowledge of the names that have been bound. And we can ask in the context of a macro with syntax local value to look up in that environment and find out what we know about this name. So in this case, we're going to look up and we're going to say if it's one of these special structure types that we put in here, this column binding or rep, then this was a valid reference. And so we want to expand to the quoted name that is going to be used in our embedding. And this would work, but this wouldn't work for DrRacket. So we're taking over responsibility from DrRacket, or from the Racket expander, for expanding this reference. And so now we have to implement the protocol that communicates to DrRacket that even though this wasn't a Racket reference, it was a reference, and I want you to draw an arrow. So that's what's going on with this syntax property. We have to attach to the syntax that we generate the fact that this was a reference that disappeared. It's not in the compiled syntax anymore as a reference. But we still want to draw an arrow. So we attach the syntax property. So this was our second strategy. Use recursive macros to enforce the grammar. Bind DSL names with let syntax. We're reusing a bit of Racket there because let syntax is going to do macro hygiene for us properly and things like that. And then finally, check references in this reflective way, taking over a little bit of responsibility and having to communicate to DrRacket ourselves. So things are getting a little bit more complicated. So where have we gotten with this implementation? Well, we got to misuse leading to syntax errors. We got to when we highlight, when we, 1 and 2. All right, I might have broken this implementation, so we'll look at it. So we got most of the things that we want, but the thing that we didn't get, if I ran that one, was it would still take 3 or 6 seconds or something. What we want is we want our queries to be fast, even though we aren't writing them with the where clause in the right place, right? We want our compiler to automatically do what's called predicate pushdown and move up that where before the join. So we want an implementation that can do that for us. And the problem with the recursive one that we just looked at is that this compilation, we don't know anything about the binding structure of it until we've actually compiled all the way to Racket, right? The way we're implementing binding structure is by generating these let syntaxes, by letting those let syntax bound macros expand when we get down to them. And so the problem is by the time that we understand what names that where clause refers to, it's already been compiled to Racket. It's too late to go move around the where clauses anymore. We're out of our DSL syntax. So in order to be able to actually apply this optimization here, we need a new strategy. We need a strategy where we have something like a macro expander for our DSL that's going to traverse that DSL syntax and understand its binding structure. And if we had a macro extensible DSL, actually expand those macros too. But the key piece in here is understand that binding structure and record it so that when we get to our DSL compiler and we want to do an optimization, we can do that by transforming the DSL core language to some, move up the where clause while still in the DSL syntax. And only after that do we want to transform down to Racket. So this is what we want to do, but the tricky piece is this expander, right? Because we need a macro expander for a DSL, not a macro expander for Racket, which is what we have, right? All right, so let's look at the sort of top level of this implementation. So here's our query macro now, and it proceeds in sort of 3 steps. The first is that it takes our original query syntax, and it passes it to something called expand query, which does something like what the Racket macro expander does, but for our DSL syntax. So the thing that comes out is still structured like a query. Still has a from clause, still has other clauses. So then we're going to take all of the clauses after the from clauses, that's our c hat ... and we're going to apply our predicate pushdown optimization to reorder them. So the c hat that comes back is going to have those clauses reordered. We're going to do our predicate pushdown and push up the where clause up before the join. And then finally, we'll do our code generation here, right? So this is a really conventional feeling compiler pipeline. We have our front end that does some analysis, sort of our middle end that does some optimization, our back end that generates code in our target language. So that's the architecture that we want. The problem is writing this DSL expander. So I've written it here. We have sort of an expand function for each grammar non-terminal. And I'll just open one to give a sense of what this feels like. So there's a bunch of sort of operations here, and they're all interacting with sort of the data representations that the expander uses under the hood for the expander environment and for scope sets. So making a definition context is saying we're going to add something to the expander environment. Internal definition, let's see, syntax local bind syntaxes says here's a particular binding that we want to add to that part of the expander environment. Internal definition context says add scopes, says we're going to paint some scopes for scope sets hygiene. And we have to do all of these things sort of at the right time and to the right syntax. So there's another little bit of complication here. Because of the way we want the name is bound by from to be visible in the clauses after from, we have to pass them in and out of this expand function for from. So this nested variable has all of the later clauses in the query. We pass them in so that we can paint the scope on them here for scope sets hygiene, and we pass them back out so that the next clause can do the same thing. So I'm not asking you to exactly understand what's going on here. The high level idea is just we're interacting with those lower level expander representations in order to implement our own expander that cooperates with the host language expander. And if we do that, we get this architecture that lets us have our optimizations that we really, really want. But this is quite a challenge. So that's what Syntax-spec does for you. So with Syntax-spec, I want to look at the implementation. The idea of having an expander from the DSL surface to core that checks syntax is going to be the same, but instead of handwriting that expander, we're going to generate it from a declarative specification of the DSL syntax. So we're going to write these 25 lines, and it's going to generate those 100 lines of DSL expander code. And these 25 lines are much more what you might expect when you're making a DSL. So we're going to have an entry point to the DSL, that's query, and then we're going to have a grammar with 3 different non-terminals for from clauses, and we're also going to have the kind of binding for our call hooks. And then in each of these non-terminals, we're just going to have the production. So we're going to say, well, we have a select, we have a where, we have a join, we're providing a grammar, right? And then we add a little bit onto that grammar. We're going to add these scoping annotations so that the expander knows how to check binding and knows how to implement macro hygiene. And then it's going to be able to generate that expander for us. And so our top-level compiled query is just, apply predicate pushdown, do the code generation. And there are a number of other patterns I didn't get the chance to show you that in the manual expander implementation you sort of had to do. We still had to record disappeared uses for the IDE. We had some other tricks to integrate the expansion and compilation processes, and Syntax-spec sort of takes care of all of that for you. So we saw these 4 different ways of implementing your DSL, starting from the familiar, which is macro embedding, macro per DSL element, And here you can hide parts of the syntax that you find unpleasant, but you can't implement these more global checks, right? With recursive rewriting, we could implement a global check, we could implement binding, but our problem was that we were interpreting inter-racket syntax immediately. We didn't have an opportunity to transform at the level of DSL syntax. So to do that, if we want to transform at the DSL syntax, we have to implement our front end as this DSL macro expander, and that requires sort of a low-level understanding of Racket's sort of syntax model. And the alternative is to use Syntax-spec that generates that from a high-level specification. That's it. Oh, and if you want to see the code, it's online. So.
Awesome. Thank you, Michael. I think we've got time for maybe just a quick question. Sort of sad somebody else had one because I was going to pepper him.
That looks really neat. I didn't catch why it's not possible to optimize using the recursive rewriting.
Yeah, so the problem with recursive rewriting is that as soon as we're starting to interpret any part of the syntax, we're compiling it into Racket already. So in order to implement the binding structure of from, we compiled it to a Racket-lent syntax. And by the time we do that, by the time we understand the binding structure by compiling it into Racket binding structure, it's too late to go back and make a different decision about how to compile, to go reorder something.
You could still shovel around the code, right, though?
So we could compile to Racket, and then we could go pull the Racket back apart and move it around.
I mean, the Racket's just another syntax object.
Yes, so we could sort of abuse the Racket syntax by compiling to an embedding in the Racket syntax and moving that around, right? But then we've created this impedance where instead of thinking in terms of our DSL syntax, we've had to think in terms of an encoding in Racket syntax already, which is something that is nicer to avoid. Ask Steven. He had to represent types as Racket structures and lambdas in Turnstile.
Fair enough. It's more a question out of curiosity than arguing that syntax-spec is simpler.
Yeah, no, it's not impossible. It's absolutely not impossible, but I think it's quite unpleasant to try and do it that way.
All righty. Well, thank you, Michael. Let's thank our speaker one more time.